Welcome to the second lecture on the topic of message passing paradigm using MPI on distributed memory systems. So, in the previous lecture, we discussed about the send and receive protocols, the blockings protocols, non-blocking, buffered as well as the non-buffered protocols. So today we are going to focus on MPI, how we use MPI and how we can write simple codes and what are the important calls, function calls and subroutines in MPI. So let us quickly recall what we have discussed in the previous lecture. MPI stands for Message Passing Interface. So this is not a language. It's basically a library of subroutine and functions. It has many functions, but we can just learn some of the most important routines or the functions and which are very useful to write even complicated MPI based programs. So you can always write your programs in C, and you can use this MPI library. So the basically what we do, we generally develop a serial code, and then we develop a parallel code using MPI, and then we can compare whether both the codes are giving similar results or not, and how much speed up we are getting. When you compile a MPI program, you have to use some special flags, and of course, the MPI framework has to be installed on your machine. Uh, so let us first understand the first few important routines. Maybe we can just focus on the six most important routines, and these are very useful to write even very complicated applications. So, and we'll see that in the first three examples, we'll be just using these six routines, and how we can start from a very simple program to we can go to a relatively complicated program. So this is how a typical MPI program structure looks like. So you can say that there are four important parts. The first requirement is like you have to include some of the header files so that you can call those message passing subroutines, and all the data types, constants which are associated with MPI can be called in your program. The second step is to initialize the MPI environment, and when you initialize something, you need to also terminate that. So you can see the last one is terminate MPI environment. So you are initializing the MPI environment, and then finally you are terminating the MPI environment. In between, you can call the message passing calls. So you can see message passing calls. So they are involved in the real message passing procedure. All MPI routines, data types, and constants are prefixed by MPI underscore. So when you are using a particular call or a particular data style, you have to always prefix it by this MPI underscore. Return code for successful completion of the program is MPI success. So here also you can see it has been prefixed by MPI underscore. So the first six important MPI functions. Uh, the first one is MPI init, then MPI finalize, then you can see MPI communicator size. We'll discuss these things in detail, and then send and receive. So let us first look into the this MPI init and finalize. Before we go there, let us understand that MPI is a process oriented program. So basically it consists multiple processes, and each corresponds to one processor. Um, so this is a little different from what we discussed during our shared memory system discussions, which was more a thread oriented. So this is a process oriented. So it consists of multiple processes, and each process corresponds to a particular processor. As we discussed earlier, that both the kind of programs, I mean single program, multiple data, or even MPMD, that is multiple program, multiple data, um, can be executed using this MPI framework. But in practice, generally we use SPMD. So each process runs each process basically runs the same copy of the same code. So MPI process and threads, which we can say it's kind of a hybrid programming. So MPI process can contain a single thread, or it can even have multiple threads. So you have a process which is MPI process, and then under that process you can have multiple threads as well. MPI processes are identified by their ranks. So each process has a unique rank. If total number of processes in a particular computation is n procs, we denote that by n procs, then the rank ranges from 0 to n procs minus 1. So suppose there are 10 processes, so the ranks which will be generated, or the ranks will basically range between 0 to 9, so 10 minus 1. And this number of processes does not change during the computation. Okay, now let's go to the first example. So here you can see the first part consists of the inclusion of the header files. So that was what because we discussed here, that MPI include file, the header file. So that is what you can see here, MPI.h. So you need to include this header file so that these subroutines and functions can be utilized. Now, as we discussed, we are going to first understand the first six calls. So, in this particular example, you have four calls. So, the first one you can see here is MPI init, so which is basically initializing the MPI environment. And as we discussed, whenever you initialize the MPI environment, you need to terminate it, and we do that using MPI finalize. Now what this particular example is doing, or if you execute this particular code, what will be the output? So here you can see two variables, both are integer. One is my rank, and the second one is n proc, so that is number of processes. So once you have initialized the environment, you can always uh, look into these details of these attributes here. But what is important is once you have initialized the MPI environment, you are calling to other MPI functions, which is MPI comp rank and MPI comp size. And if you look into these attributes, you can see in both this is common, MPI com world. However, these two are changing. So in the first one, you have when you are calling MPI com rank, you have something called my rank, and then here number of processes, which is the size. We will come to this in our next slides, what this particular what these two calls basically do for you. So the output which you are going to get is because this part of the code is going to be executed by all the processes, because as we discussed, MPI is basically a process based. So each process will output uh, uh, this is which process. So say this is process 2, and it will also tell that how many processes are involved. So each process will print this, that this is process 1 among 10 processes. So process 2 will say that this is process 2 among 10 processes, and so on. And then you can finalize that. Okay. So if you remember the that particular program structure, so MPI environment basically consists of these important calls. So MPI init, MPI initialization, MPI finalize, and MPI comp size, comp rank, which we'll discuss. And there is another in important call which we call MPI underscore W time. So it basically returns an elapsed wall clock time in seconds on the calling processes. And this kind of functions you have used while doing OpenMP also. So to measure the time. Now, if we look into the MPI init into a little more details, so what it basically does, it initializes MPI environment. It must be called before any other MPI routine, and it is only called once. Subsequent calls will lead to error. And whenever you initialize the MPI environment, we need to terminate that, and we achieve that through MPI finalize call. So it basically cleans up the MPI environment. This must be called before exit. No other MPI call can be called after this MPI finalize call. No other MPI routine. You can always, do other things in the code, but not any MPI routine. There are some exceptions to this. For example, MPI initialized, MPI get version, and MPI finalized. We can look into these details later on, because currently we just want to focus on the most important calls which can be utilized to write very important codes. Abnormal termination, you can call MPI abort, and it basically can be used to abort all tasks. Now, in the first example, we have seen that we have used two calls, the MPI com size and MPI com rank. So if you go to this example, you can see MPI com rank and MPI com size. So now we are going to understand the utility of these two calls, because you have already understood the MPI init and MPI finalize. So when in MPI, basically we are dealing with a set of processes, and we want to initiate some kind of communication among these processes. So we define a communicator. We also call it a communication domain, and this communication domain basically contains a set of processes that are allowed to communicate with each other. Now suppose you have 10 processes, you can always create a small communication domain which may consist just 5 of those processes. So out of 10 you can just select 5 processes and make a communication domain out of those 5 processes, and then these processes are allowed to communicate with each other. So communication among those five processes which are part of that communication domain. So they cannot communicate with a process which is not a part of that communication domain. Now, information about communication domains is stored in variables of type MPI com. So you can see uh, whenever you write MPI com, then you can get several information related to this communication domain. What is the size of that communication domain? What is the rank of a particular process in that communication domain? Okay, so communicators are used as arguments to all message transfer routines. So till now, in the first example, we have not discussed anything about transfer of data. So we have simply initialized the MPI environment and finalized it, and in between we are just testing the environment. I mean, what is the rank of a particular process in that communicator, how many processes are there, but as such no communication is taking place. I mean, no transfer of message is taking place in this particular example. But in most of the programs, I mean in real programs, the main goal is to actually do some kind of communication in terms of message transfer. So whenever we do any kind of message transfer from one process to another, we use these communicators as arguments. Now a process can belong to many different communication domains. So we are free to create more than one communication domain. So suppose there is a process N, or let's say process 2, so that can be a part of two communication domains. So you can distinguish from this communication domain name, basically it belongs to which communication domain. MPI defines a default communicator or a communication domain, which we call MPI com world, and which by default includes all processes. So if you look into the first example, you can see MPI com world. So that's the communication domain. So by default, it is going to include all the processes involved in this particular program. So when you execute the code in the very beginning, you will, I mean, you can explicitly tell, I mean, on how many processors this program is going to be executed. I mean, on how many processors you plan to execute this code, and all processes will belong to this default communicator MPI com world. So in the very beginning, if we wish that this program is going to be executed on 10 processors, so all the 10 processes are part of this MPI com world. And then we can always define other communication domains, which can consist of less number of processes, and they can be given different name. So by default, we always have MPI com world, which includes all the processes. MPI com size basically returns you the number of processes in the group or the communication domain associated with a particular communication domain. MPI com rank determines the rank of the calling process, because this MPI com rank can be called from different processes. So whichever process is calling this MPI com rank function, So it will determine or it will return the rank of the calling process within that communicator. So if we look into this first example, so in this case the default communication is MPI com world, and say process 1 is calling this, then what you are going to get here is that my rank is 1. So 1 will be returned here. And again, this is also, suppose process 1 is calling this MPI com size, it will return how many processes are there. So this particular return is going to be same from all the process, but this is going to change as you go from one process to the another process. So now we know that MPI com rank basically determines the rank of a particular process in a communicator, and the size, MPI com size, determines the size of the communicator. So these two important questions have been addressed using these two important calls. So how many CPUs, that is addressed by MPI com size, and who am I, what is my rank, so that is addressed by MPI com rank. Now these two are very useful and can be used for data decomposition, because as we have learned in our previous lectures, data decomposition is a very important step in parallelization. So suppose we are working on a problem which consists of several grid points, and we know that how many grid points are there. We also know how many CPUs are there and what is the current CPU ID. So we can always calculate which portion of data can be associated with the current CPU. So suppose you have n grid points and total number of CPUs is 10. So you can always divide the total data, that is n grid points, among 10 CPUs, and each of the CPU is going to get n by 10 amount of work, and then you exactly know which part of the data is going to go into which of the processes, because you know the rank. So ranks used to specify, and also these ranks can be used to specify source and destination of communications when you are doing actual send receive communications. We can look into that in our second example. So my rank value is different on different processors. It's unique. So now let's look into the second example, and here we are going to use two additional functions, because we have already seen this that how we have used these first four functions in our first example, but now we are going to also use MPI send and receive, which is actually responsible for message transfer. So in this particular example, first step is definitely including the header file MPIH. Then you can initiate the environment MPI by using the MPI init function, and as we done in our previous example, you have to terminate the MPI environment by using a MPI finalize call at the end. Now in between, you are using MPI comp rank, so this will help in getting the rank of a particular process. And once the process knows what is its rank, it exactly know what it is supposed to do. So suppose there are n processes. Now if the rank is 0, then what we are doing is that we are initiating a send call. So if the rank is 0, you are writing the code in such a way that a send will be initiated, from rank 0 to rank 1, because here it is said 1, but you can also do it to other ranks. But in this particular example, let's assume there are only two processes, so 0 and 1. So 0 is sending the message and 1 is receiving the message. So what we are sending here, we are sending a character variable. So we'll go into the details of these attributes, because these are standard attributes. I mean, the number of attributes and the order is very important, in which order they are supposed to be written. So the important thing is that based on this rank, we can explicitly mention which process is going to be the sending process, and which process is going to receive the message. So here you are sending a character message and you are receiving the same message. So 0 is sending and 1 is receiving. Now there are two broad kind of communications in MPI. One is point to point communication. So that is exactly what we have seen in the second example. So it is like a point to point communication. So you are going from 0 to 1. So send and receive between 0 to 1. But we can also do collective communications. So these communications involves all the processes within a communicator. So all the processes within a communicator participate in communication, because in point to point communications, it simply involves the sender and receiver. So one processor to another processor. So in this particular example, you may have more than two processes, but only process 0 and process 1 is involved in this message transfer. Okay, but in collective communications, all processes will participate. Here only the two processes participate in communication, and we explicitly mention that, like which process is the sender process and which is the receiver process. Now let's look into the arguments of MPI send and MPI receive, and what are the questions which we need to address, and how those questions are actually addressed using these arguments. So the first thing is message data. I mean, what to send and what to receive. So this is the message. So in this particular example, we are sending a character message. So you can see here this character message. Okay, so we are basically sending this message here. So the first argument is what to send, so that is this message. The second argument is what is the size of that message. Okay, the third one is what is the data type. So in this case it is character, and it is prefixed with the MPI underscore. As we mentioned earlier, that all MPI data types needs to be prefixed with an MPI underscore. The fourth one is who is going to receive the message. So that's 1. So 0 is sending and 1 is going to receive. The next one is some kind of tag. So suppose you are sending several such messages between 0 to 1. So we need to know, or we need to keep track of which message we are talking about. So these tags can be used to identify different messages. And MPI COM world is the default communicator, which includes all the processes. So definitely 0 and 1 is a part of this communicator. So the message envelope basically contains this information, that is where to send. Like you can see one here, so that's the receiving process. So it tells you the information about sender and receiver, what is the context of the communication, and what is the tag. So like this 99 is the tag. Now if you compare these two calls, you will see the first is similar in both the cases, message message. The second is the length of the message which is to be sent by the sender, and similarly it also tells you the length of the message to be received. Need not be exactly same, but there are certain constants we are going to discuss in next slides. The third one is the data type in both the cases. Fourth one is basically in the case of send, it is going to specify where the message is supposed to go, and in case of receive we need to specify from where we are getting the message. So you can see it is 1 here, so it is going from 0 to 1, and it is 0 here, but it is because we are receiving from 0. And the this is the tag which is same in both the cases. Then we have this communicator which is same in both the cases, MPI combo, the default communicator. However, you can see that there is an extra argument here which is status, and this is very important. We'll see what is the importance of this particular argument. So let's once again focus on send. These two calls, the MPI send and MPI receive, is very very important. So if we understand this, I mean, we can do even complicated MPI programming. So the first one is the buffer, the memory address of start of the message. So this is actually associated with the message. So buffer actually tells you the memory address of start of message. Then the second one is the number of data items. This is an integer because this is a kind of a count. So even if you go back here in this one, so you can see it was 256. Here it is, I mean str length. So here you can go and see that this this is the message. So this hello, and so you can counting the length of this message. So we can see that the second one is basically integer. So how many data items? The third one is data type, which can be integer, character, double, floor, whatever. The fourth one we have already discussed, the destination. Then there is tag, additional identification of message, and then communicator. Now let's look into the receive call. So what is different from the send call is this status argument. So this is a object which contains some additional info regarding the received message. So the actual number of data items received can be queried from this status object. It may be smaller than count, um, but cannot be larger. So so this one, because we are using a count here, so this number has to be I mean consistent with the size of the message which we are sending. Okay. And whether the message has been successfully transferred or not can be inquired by using this particular object, because it contains very important information. I mean, we can see how this object can be used to get further information. Now these are the basic MPI data types. This you can also look into a MPI documentation uh, document which is available, or any MPI book, um, and this can be understood better when you are actually doing the coding. Now, what are the essentials of communication? Sender must specify valid destination. Whenever you are giving a send call, we need to give a valid destination. Sender and receiver data type, tag, communicator must match. So both the processes need to be a part of the same communicator. So we have seen that both are part of MPI COM world communicator. Receiver returns extra parameter, that is the status, to report information regarding the received message. Sender specifies the size of send buffer, and receiver specifies the upper bound of receive buffer. Okay, so the upper bound. That's the important point. If it is less, then there can be errors actually, and we have to be very careful about that. So this is basically the upper bound. So you cannot receive a message which is more than this upper bound. Both standard send and receive functions. So by standard we mean MPI underscore send. There are other send calls which we'll discuss later, but these two are referred to as standard calls: MPI underscore send and MPI underscore receive. Now, these two standard functions are blocking in nature. So, you have already discussed in our previous lecture what do you mean by blocking. So, MPI receive returns only after receive buffer contains the requested message. So, the receiving process, when it calls this receive function, um, it is because it is blocking in nature, so it only returns after it makes sure that the receive buffer contains the requested message. Okay, and MPI send may or may not block until message received, but generally it blocks because it's blocking in nature. Okay, now, because of its blocking nature, sometimes it may lead to deadlock, and that happens when the code is not properly written. So we'll look into a couple of examples to clarify this point, that under what situations we may encounter a deadlock. Okay, because these are blocking in nature. So as we know, in case of blocking, we want to make sure that something is guaranteed, and then only the return takes place. The CPU starts resuming what it is supposed to do next. But suppose because of some error, coding error or syntax error, uh, we are just waiting um, to satisfy that condition, and it never gets satisfied. So there may be some kind of deadlock. Okay. Now let's look into a more realistic example. We are going to take the example of trapezoidal rule, because we have already discussed this problem during our shared memory lecture. So we know how we do integration using trapezoidal rule, but once again I will briefly describe the problem. So let's assume that we have a given function, any arbitrary function, and you want to integrate this function over a problem interval a to b. So that is from start to end. So the first thing which we are supposed to do is like we need to create chunks of workload and then distribute these chunks to different processes. So each workload ideally consists of, I mean, its own sub interval A to B, uh, which are typically generally, I mean, same for load balancing purpose, and these are assigned to each process, and then we can calculate the f for each sub interval. So suppose a to big is the given problem interval, you are dividing that uh, problem interval into sub intervals and you are denoting it by small a and b, and then this job is assigned to each processes depending on how many processes you have. So that number of processes is going to determine the size of your sub interval. Now finally, when you have calculated the f for all the sub intervals, you get the final result for the whole complete interval or the complete problem. So issues to consider: load balancing, how many number of trapezoids to be produced so that it is equally divisible, because you can always have a finite number of trapezoids when you are going to divide this problem interval. Let's say that this is equally divisible across number of processors p. So let's say you have 100 trapezoids and you have 5 processes, so each one will get 20 chunks of work to uh, do. So each process needs the following information: the rank of the process, which it can always get using MPI-com rank, and ability to derive the workload per processor as a function of rank. So any of the processes can take the role of kind of a master process, and then it can do the final summation, and that information it can get by using this rank information about a particular process. So the algorithm will look like this. So this is, so in a trapezoidal rule basically you have half, I mean you are calculating the area of a given trapezoid. So this is the h, so that's basically the base actually. So this you are calculating by dividing the complete interval into n trapezoids. So I should ideally write capital B minus A, capital A, and then number of trapezoids. So that will give you H. Each process calculates its one workload. So local number of trapezoids. So local n is n by p. So you have total 100 trapezoids and p processes, then local n is 10. So each process is going to calculate the area of 10 trapezoids. And then you can always calculate the local starting point and the local ending point, because in the complete problem the starting point is A and the ending point is B, but for each problem we need to get the local starting point and the local ending point. Now each process calculates its own integral for the local intervals. Once this is done, let's assume that the process rank, the zero rank process, receives the message from all processors and then add the sub interval areas to get the final area. So if process rank is greater than 0, it just sends the sub interval area to the process rank 0. So this is what we are supposed to code using those 6 MPI calls. So those 6 MPI calls are MPI init, finalize, MPI com size, MPI com ramp, MPI send, and MPI receive. we need to include the header file, and the important data types in this case is MPI init and MPI float. So the first thing we need to mention is what is the process rank for any given process. So this my rank variable stores that information, my process rank. What is the total number of processes? What is the local? This is the left endpoint and right endpoint. This is not the local. This is the actual problem endpoint and the actual problem right endpoint. So this is the start. This is the end. So you are trying to integrate a function between 0 to 1, and the number of trapezoids are like 1024, and the base length is h. So this is fixed for all the trapezoids. So the height is going to change. So base is fixed, and then we can calculate the local a and local b and the local n, the number of trapezoids for a particular process, and then you can find the integral over the for a given process, and then the total integral can be found by summing all the local integrals. The source is the process sending integral, so the source, and the destination is 0 in this case, because the 0 is the process 0 is going to collect all the local intervals and finally going to sum it, and tag is 0. And then we have MPI status, which is basically this particular variable is used here. So we have to first initialize, just look into this. So this is the function which calculates the local integral, and the inputs which it takes is local a, local b, and the local n. So the number of trapezoids which it is supposed to take care, and h, that's the base length, and then it will output the uh, local integral for this local a and local b. So the sum for this n local n number of trapezoids. So we initialize the MPI environment, then we get the process rank. So we know what is the rank of a particular process. We can also find out how many processes are being used. Then we can calculate the base, which is b minus a divided by n, and the local n, so that the load balancing is proper. The once these informations are here, we can always calculate local a and local b and pass it to this function trap here, and that will calculate the local integral for a given process. Once we have calculated that for each processes, now we are going to uh, I mean mention clearly that if the rank is 0, then it is going to receive. So you can see if my rank is 0, there is no send statement here, it's simply the receive. So it is receiving from all other processes. So all other processes are going to start from 1 because this rank is 0, and total number of processes are uh, p minus 1 basically. So that's why it goes from 1 to p minus 1, and that is what the source we are going to put here. So that's the um, the source. So this is the destination. So MPI is basically receiving from all other processes, and the rank of those processes are being provided through this source variable. And you can see the first one is basically integral, which has been calculated by each processes. The size is 1, the count, and its float, the data type. all the processes are part of this communicator, that is MPI COM word. And so you can get the total one by one. You are going to receive this data from all other processes other than 0, and then you are going to add it to this variable which is total. And if the rank is not 0, then all the processes are going to send its local integral which it has calculated to this destination. So in this case the destination is 0, which we have already mentioned. Here you can see the destination is 0. So when you look into this MPI send, all processes are basically sending it to this destination 0. And then once this is done, we can always get the final result, and then we can terminate the MPI environment. What is important to understand is that these two calls are blocking in nature, MPI receive and MPI send. So we need to make sure that there is no deadlock as such. Here we are not going to get any deadlock, but we'll see under what circumstances we may end up with a deadlock situation. So let us summarize what we have learned till now. So we have seen that MPI programs are made up of communicating processes. So basically, communication takes place among many processes which are involved. Each process has its own address space. It contains its own attributes such as rank, size, etc. Default communication is MPI COM world. All processes are its members. It has a size, so the number of processes which are involved in that particular program, and each process has a rank within it. And then we can use these send receive functions to communicate among processes. Now these send receive functions can use different protocols which we have discussed in our previous lecture, like it can be blocking in nature, non-blocking. So today we have used the standard MPI send and receive, and both are blocking in nature. In our next lecture, we'll see what kind of deadlock um, can happen if we uh, do not take care of those situations which may lead to deadlock, particularly with calls which are blocking in nature. Okay, see you in next lecture.